let's do some more inverse trig functions. That's what we're talking about. Now, we've talked about sine and cosine, inverse sine and inverse cosine. I think it's only natural to talk the next about inverse tangent. Actually, for kind of surprising, maybe, the inverse tangent is actually kind of the best one. It is the one which is nicest in a certain ways, which you'll see in a moment. This is a true fact. I was sitting at home last night watching WandaVision with my family.
Wait, did you watch the newest episode?
No, we're a little behind, so don't spoil it.
One came out this morning. I was gonna watch it, but I didn't.
Oh, today? Yeah. We watched episode 5, and I won't spoil it for anybody, but did you notice in episode 5, there was an appearance of the inverse tangent. There was like a whiteboard in the background with a bunch of nonsense math written on it, and it had two inverse tangents written on it. As far as I can tell, it was totally meaningless. I sometimes enjoy looking at this sort of Hollywood math. It's usually just, they write things that look kind of crazy, but they don't actually mean anything. And this, I think, I mean, as far as I could tell, this was another example. But it's always nice to see what the Hollywood types think looks cool. And apparently, the inverse tangent is making the rounds. If they had put like the inverse sine or inverse cosine, to me, those are more complicated. Like I said, the inverse tangent is less complicated than the other ones. I would have been more impressed to see something like the inverse cosecant, but they didn't go there. The inverse tangent, what makes it better than the other ones? Remember, all of these come from looking at a piece of the original function. So we're going to look at the graph of tangent of x. And the graph of tangent of x is kind of notoriously weird, but it turns out to invert nicer than the other ones. So this is what the graph of tan x looks like. It has sort of recurring asymptotes like this. And these asymptotes are at pi over 2 and minus pi over 2. And then the next one is at 3 pi over 2. But, anyway, tangent, just like all the other ones, does not have a true inverse because it's not one-to-one. And so we choose a piece of it which we are going to, we choose a piece which is one-to-one and then invert that piece. And in this case, I think it's pretty clear. You should choose something like this, right? And when I invert this, it makes a very nice looking function. So this piece, I will say, this piece has a domain minus pi over 2 to pi over 2. And this is the open interval because you're not actually allowed to plug in pi over 2 and minus pi over 2 to the tangent because that gives you a 0 in the denominator. But all the other, the numbers in between. And then the range of this is all real numbers, right? Minus infinity to infinity. That is the set of y values that you can get as the answer of the tangent. You can get any number. And so when we invert this piece, just like all the other examples. But the piece is kind of nicer in this case than the sine or the cosine. What you get is a function that has, instead of those vertical asymptotes, they are horizontal asymptotes at pi over 2 up here and minus pi over 2 down here. And we get this curve. It looks like this. It's a little lumpy on the left side. It's not supposed to be lumpy like that. This is inverse tangent of x, or arctangent. In my opinion, I think arctan looks kind of cooler when you write it, but actually on WandaVision they wrote it with the little inverse sign. I went to grad school at UCLA, and one of my professors worked as like a Hollywood math consultant, which I thought was pretty cool. But I think no. This was like a little after. Mean Girls was a little before He worked on A Beautiful Mind, which was a Russell Crowe movie. Yeah. He was apparently, I think usually like if they want like a blackboard full of math, they just write a bunch of nonsense. But for A Beautiful Mind, they really wanted it to be authentic, and so my professor actually like spent time training Russell Crowe how to. They had the script, but like when an actor is reading a bunch of math, they don't really know how to say it or how to emphasize what would make sense. So he kind of he didn't. Yeah, I don't think he actually learned what it meant, what he was saying, but he at least learned like grammatically how to say it in a sensible way. Uh, yeah, he actually, my professor, during class one day, his phone rang, um, and he answered it during class, and we were all kind of like, "What is going on?" And he said hello, and as he's talking on the phone, he writes on the blackboard, Russell Crowe, to make sure that we all knew that it was Russell Crowe. That's not how you spell Crowe, I know. It was a very awkward moment. Like we learned as he's talking to Russell Crowe on the phone, that like my professor, his wife had died like the day before or something, and Russell Crowe was calling him to say, and I guess like he knew ahead of time that Russell Crowe was going to call him, so he had his phone turned on. But we didn't.
Every single class. It's so funny. It's just a landline. He'll be like sitting in class, macroeconomics, blah, blah, blah. And it would just like right on the side, and it would go like 3-4 times in class. It's so funny.
Uh-huh. All right, let's talk about the arctan. So, yeah, this one is nicer than the other ones just because its domain is all real numbers, right? So you can it's a nice function. You don't have to worry about what kinds of values am I allowed to plug into this in the way that you do with sine, the inverse sine and the inverse cosine. And the range, of course, is minus pi over 2 to pi over 2. All right. And you know we've been through this so often with the sine and the cosine. The next thing that we would talk about here is finding the derivative of the inverse tangent. And rather than going through the details, you know, the way to do it is by writing it again as the tangent and then doing the implicit derivative. We did this last time and the time before with sine and cosine. So would you mind if I just told you? So I will say similarly, we can find the derivative of the inverse tangent, and I will tell you what you get, and it's a nicer formula than the sine or cosine ones. 1 over 1 plus x squared. This is the derivative of the arctangent. The way you would figure this out is exactly like we did for the sine and cosine. I don't think we need to go through the details. I will just refresh your memory that the derivative of this, the arcsine, or the inverse sine, is 1 over the square root of 1 minus x squared, which is a little more taxing to deal with. But the arctangent one is nicer. All right. So, for example, we can do, what's the derivative of, you know, the inverse tangent of, let's say, 5x squared? How would you do that? Well, you got to use the chain rule, but you basically use the formula in the box there, using, instead of x, using 5x squared. So you go 1 over 1 plus, this is a little weird, but 5x squared, right? You got 2 squares there because one of these squares is built into the derivative formula. And then the inner one is because what I'm using for x already has a square in it. And then I got to do the chain rule, right? We always multiply times the derivative of the inside being 5x squared. The derivative of that is 10x. So this is the derivative of that thing. right?
Why did it change that?
Whenever you use one of these derivative formulas, this is the formula which works exactly when it's just x in here. If you ever have anything other than just x, you always have to multiply by the derivative of the inside.
So hypothetically, if you say you forgot this formula, could you do the derivative of cosine over sine, and then do?
Yeah, this is a good idea. Ordinarily speaking, I never really memorize things about tangent because you can always rewrite tangent as sine over cosine. This is not true though of the inverses. So when you invert them, this is not, just because of the, oops, that's not what I meant, but
So it wouldn't be cosine over sine.
it's definitely not that.
Okay.
It's not any of those.
Okay.
Yeah. Because the
This isn't the same as cosine,
inverse tangent is not the same as cotangent either. Yeah, cotangent is cosine over sine. The inverse tangent is something completely different. I got a few for you to try, and I think probably my I got to do that thing with the test. I'll be right with you, Gwen, if you're there. How about these? Try these in derivatives. See what you think. Derivative of, and here, maybe you can remember from last time the formulas for these. I hope you do. You don't have to remember these, but I hope you have it written down. No, but oh, she's not here. I will tell you specifically, but there. So I'm not big on making people memorize things in general. So for the test, there are some things I'll expect you to remember, but other things I'm just going to give you like a list of formulas to use during the test. And I will show you ahead of time, you know, exactly what's on the list. So you can't have your own notes, but I'll sort of make a note card for us all.
Is the first one arctan to the negative 3x?
Sorry, say that again?
Is the first one, the questions arctan to the negative 3x?
Negative 8x. Yeah. Sorry if it's hard to read. Hey, Gwen, I see you there. I'm gonna.
Sorry, I couldn't find this.
No problem. I just assigned you to a room. You all ready, Gwen?
Yeah, for the test, I didn't get the email yet.
Yeah, I'm gonna send it to you through Zoom. All right, I just sent it. Can you see it?
Yeah, alright, perfect. Just downloaded it.
Okay, great. So yeah, I will be unavailable for questions until around 11, but hopefully that's all right. All right. Okay. Sorry for the interruption, but we were working on these anyway. I think I'm ready to talk about these. I hope that you worked them out. So the first one is very similar to what I did before. This would be 1 over 1 plus negative 8x squared times negative 8, right? I hope that's what you got. That times negative 8 at the end is the chain rule. That's the derivative of the inside of the parentheses. Any questions about that one? All right. The next one, inverse cosine of root x. So you have to, look up from last time the derivative of inverse cosine is 1 over minus root 1 minus x squared. It's the same derivative as the derivative of inverse sine. It's just it has this negative sign, which does not appear in the derivative of inverse sine. That's because actually the graphs of those two functions, they look almost the same. One looks like this and the other looks like this. And so the slopes as you go across them, they actually are kind of the same, just they're opposites of one another. Anyway, what do we got over here? What do you say?
1 over negative square root 1 minus x, right? Since the 1 half and square root.
Yeah. Yeah, great. Excellent. Yeah, this is just x in here because it ends up being root x, but then you square it, so you end up with just x in there. And then don't forget this guy is the chain rule part. Everybody good with that one? All right, excellent. And how about this one? Inverse sine of 4 to the power x.
This one's going to be using the sine formula, which is 1 over the square root of 1 minus x squared. So
Yep.
for that x squared, you're inserting 4 to the x.
Uh-huh.
And you're also going to have to multiply that by 4x to the x minus 1.
Yeah, so this is the part that you get directly from plugging into the formula. And then times the chain rule, you want the derivative of 4 to the power x. This actually is not 4 to the...
Because you bring the x in front. Or 4 to the x to the x minus 1.
It's not that. This is a exponential function. When the x is inside the exponent, there's a totally different rule about this. So this would be somewhere in your notes. You should have a formula about this. Anyone actually remember this one?
Oh, b to the x is b to the ln x?
Yeah, it's b to the x ln b is what you do. So that's what you got to do here. 4 to the x ln 4. So that goes here. There you go. So, all right. There's a lot of ins and outs. Any questions from the folks back home? I have a hard time hearing the folks back home. I don't know why I turn my sound all the way up and it's not good enough. All right, great. Last thing I want to say about the inverse trig functions is they actually give us some useful new integral formulas. The first one actually is turns out to be not as useful, but anyway, the derivative of inverse sine is 1 over 1 square root 1 minus x squared, right? And that means you can rewrite this as an integral. It means the integral of this thing, 1 over square root 1 minus x squared dx, is inverse sine of x plus c, right? And this is a new integral formula. This integral here is not one that you can do by any other method. If you just saw that integral, you can't do a u substitution to figure out what it is. It turns out, this is what it is. It's the inverse sine of x. And the inverse cosine gives you basically the same integral formula, so we usually don't even talk about that, but this one is interesting. The derivative of inverse tangent is 1 over 1 plus x squared. And this gives us the integration formula 1 over 1 plus x squared dx. The integral of that is the inverse tangent. And that one turns out to be come up every so often, a little more commonly than I mean, the one for the inverse sine is a little more obscure, but the inverse tangent one is fairly ordinary looking function there. And it turns out the integral is inverse tangent. Pretty weird because the thing on the left side of that integral has nothing to do with trigonometry at all. At least it doesn't seem to. 1 over 1 plus x squared. But the integral is the inverse tangent. So let's try some simple examples with this. How about... Yeah, so I will write the cosine one, but we actually are never going to use the cosine one. And maybe I'll say why also. So I'll write the cosine one in blue to indicate that this doesn't really deserve a place in the formula lists. No offense if your dad invented the inverse cosine. It means this. Right? The reason why this is not typically written down as a useful formula is because this part is really the same as this, except for the minus sign. That's the only difference. But if you were actually finding the integral of this, I would just factor the minus sign out of the integral and then use this formula, right? So there isn't really a good reason to use this formula by itself, because you would always, if you ever had to do this integral, I mean, to me at least, I would just factor the minus sign out of the integral. Yeah, right. No, I don't know what you mean, but I'm not.
Maybe I'm just confused, but if you're saying that we're not going to need to know the cosine function, or the integral of the cosine, because it's similar to the integral of the sine, but we're going to have to learn how to convert from the sine to the cosine or not?
No. Like, when these are formulas about the integral, so you have to imagine the reason you would want to use these integral formulas is if for some reason you came across an integral that looks like 1 over the square root of something or other. And such a thing, you do the integral as an inverse sine. There is no scenario in which you would have to do this and come up with an inverse cosine, because you can always factor the minus sign out and make it an inverse sine. The fact that these two are almost the same suggests that there's some kind of hidden relationship between the inverse sine and the inverse cosine. Like those functions themselves are related, and they are related. They have kind of the same derivative, which means they differ by a constant. But I don't care about that. Yeah, we're not going to go there. All right, excellent. Let's talk about. Oh yeah, I just wanted to do some examples. So, first of all, simple example. Simple meaning we're just basically going to plug into the formula as is for this one. What is the integral from 0 to 1? 1 over 1 plus x squared dx. So when you see 1 over 1 plus x squared, you should just immediately use the integral formula that you see up here for the arctangent, the inverse tangent. All right, we get inverse tan x, and we're going to plug in 0 and 1. All right. Now we can actually, let's try and work this out. So this means inverse tan of 1 minus inverse tan of 0. Can we figure those out? You know, you could type this into your calculator. Your calculator probably has an inverse tan function in there somewhere. Maybe not, it's on its own button, but can we figure these out? Inverse tan of 1. That means it is an angle whose tangent is 1. Any angle masters out there? Remember an angle where the tangent is 1? You could think of this in terms of a triangle. We want the opposite over the adjacent to be 1, right? What angle has that property? On this picture, if you want the opposite over the adjacent to equal 1, that is to say that the opposite and the adjacent are the same, right? So that when you divide them, you get 1. So what angle does this need to be? If these two sides are going to be the same. Yeah, this is a 45-degree angle if you want those two sides to be equal to each other. So that would be pi over 4 is the arctangent of 1. So that where this comes from, I don't care how you arrive at this realization, but it's because tan of pi over 4 equals 1. So maybe you just have the values of tangent memorized, or I don't myself have them memorized per se, but you should be able to think through it somehow and figure out that pi over 4 is the angle you're looking for, which has tangent equal to 1. And then for this one, arctan of 0, inverse tangent of 0. Anybody recall what's an angle whose tangent is 0? Yeah, right. The graph of tangent looks like that. It goes through the origin. The graph of arctangent, if you want to draw the inverse tangent graph, it goes through the origin. Yeah, this is 0. This is because tan of 0 equals 0. This I can remember because tan is sine over cosine, and I know that sine of 0 is 0, so tangent of 0 must also be 0. All right. Anyway, my final answer then is pi over 4. Right? Sort of weird, in my opinion, that you start with this thing, which doesn't seem to have anything to do with trigonometry at all, and you get pi over 4 for the answer, which is interesting. I would expect you to be able to do that, and I would tell you specifically, like simplify any trig functions in your answer, something like that. Yeah. Yeah. Sorry, that's not what you wanted to hear. Huh? Sorry, not sorry. Okay, some variations on this. You can actually use this arctan and the arcsine formulas to do some similar ones, but ones which are not quite the same. So some tricks to do other similar looking but not quite the same integrals. How about this? 1 over 1 minus 4x squared. Now, when I see this, I immediately think of the inverse sine formula. So this one is, it sort of looks like, it looks similar to this one, 1 over square root 1 minus x squared dx, right? So when you see this this thing on the left side, what should come to your mind is this formula about the this one, which equals the inverse sine of x plus c. We would like to do something to kind of make it fit the format that you see over here. And the problem really is this extra 4 there. How do we going to handle that? Now, in some situations, I would try to just pull this all the way out of the integral, but you can't do that here. It's stuck inside the square root, and also it's only on this x squared part, so you cannot factor it all the way out of the integral. Anybody got another suggestion? Handle the 4? This is not terribly obvious, but you could try to, say, maybe multiply everything by 1/4 to cancel that 4 out. The problem with that is it will mess up the 1 and turn it into a 1/4, and then you can't. That's kind of even worse to use this formula over here. Here's the trick.
Could you give it its own square root?
Maybe. So what do you mean by that?
So take the 4 out and just 1 would be like 1 minus x squared minus square root of 4.
Can't exactly do that. He said make the 4 into its own square root or something. Here's this is the idea that you want to do. Shove the 4 into the square. Can we rewrite it somehow like that? Yes. How would you? Yeah. 4x squared, like it is up there, is the same as 2x the whole thing squared. This is what I thought maybe you meant by taking the, you're sort of shoving the 4 inside of the square by replacing the 4 with its own square root, which is 2. All right? And then we can do the u substitution. U equals 2x. And once you replace that 2x with the u, then it will look exactly like the integral formula that I intend to use for the inverse sine. So let's see if we can work this out. So u is 2x, that means du is 2 dx. And so this becomes 1 over square root 1 minus u squared. And then instead of, what do I do with dx? Yeah, put the 1/2 du. So this is 1/2 du equals dx. This is the trick. Now we can pull the 1/2 out of the integral. All right. And what's the integral going to be? Yes, inverse sine of u plus c. And so my final answer is 1/2 inverse sine of 2x plus c. There you go. So the trick in that case, if you have a sort of coefficient in front of the x squared, you rewrite it and shove the coefficient inside of the square so that you can then do the u substitution. Yeah. No, that's a good idea, because then you could simplify that, but this is not a true fact about square roots. Like if you have this is not equal to root a plus root b, which I think that's what you just said, right? Yeah, you can't do that with square roots, unfortunately, because like, you know, something like square root of 9 plus 16 is the square root of 25, which is 5. But if you root each of these, you would get root 9 plus root 16, which is 3 plus 4, which is 7. So they're not the same.
If it was like square root a b, you could do square root a.
Yeah, right. That's the proper rule is this. This is true. So this is not true. This one is true. If you want to get yourself a math tattoo, get this one in the box there, not this one. You don't want to.
Theoretically, if I got a unit circle tattooed on my forearm, is that cheating if I bring it into class?
I would allow it.
I better believe I'm
Yep.
gonna get
So people have asked me that before. No one has ever actually done it. Okay, I'm open to it. All right. Okay, one more example of sort of a simple trick modification to the basic arctangent and arcsine integral formulas. So another trick, once more. That one we just did is what happens if there's like an extra coefficient in front of the x squared. You can modify that by shoving the coefficient inside of the square. What about, here's another trick. This one. What if instead of a 1 down there, it's just some other number? All right.
One down where?
Oh, well, what I mean right here. You know, we would like for this to be a 1, because this one looks like the arctangent formula. Looks like integral 1 over 1 plus x squared equals inverse tan of x, right? But what if it wasn't a 1 there? What if it was just some other number? And here I think actually maybe one of the suggestions that somebody said before will actually work in this case. We can divide everything in this whole fraction through by 16. So I'm going to write this is the same as 1 over 16 over 1 plus x squared over 16. That's the same because we just divide the top and the bottom by 16, which doesn't change the value of the fraction. And then the 1/16 up top, you can factor that all the way out of the integral, so that doesn't matter anymore in terms of figuring out how to do the integral. This looks better, right? My intention is to match it up with this over there, the inverse tangent integral formula. And I have sort of repaired this, which used to be a 16 plus, is now a 1 plus, so I like that better. How can we deal with x squared over 16? Yeah, we do the same trick. Yeah, we do the same trick we did in the previous example now. So rewrite this as 1 over 1 plus x over 4 squared, which I think may be similar to what he said too. You, just like before, you shove the extra number inside the squaring. And the purpose of that is because I intend to do u substitution now. U equals x over 4. And then it will match my inverse tangent integral formula. So from here I go u equals x over 4. That means du is 1/4 dx, which means 4 du equals dx. All right. And now we can do the usual u substitution business. 1 over 16 is just going to stay in the front. And then we go 1 over 1 plus u squared. And then dx is times 4 du, like so. Right, almost done with this. You can factor the 4 out front. It becomes 4 over 16, which of course will cancel as 1/4. 1 over 1 plus u squared du. And then that is the inverse tangent. So I'll write the 1/4 outside. Inverse tan of u plus c, and then stick it back in. 1/4 inverse tan of x over 4. That's that. All right, so these two tricks are going to come in handy. Any questions about that one? In fact, actually, if you look at this, what we started with versus what we ended up with, it's not so hard to make some kind of general conclusions about how this is going to work out in generally. Generally, there is a formula for this, 1 over a squared plus x squared dx. Like here, I had 16, which is 4 squared. The exact same trick will work no matter what that number is. If it's a square of something, you can do the same stuff that I just did, and the answer will be, anyone want to predict what the answer is in general, just based on the answer we got before? Yeah, right. A could be any constant. That's right, a constant, yeah. Yeah, right. Yep, this is the formula in general. So the example we just did was when a is 4, 16 is 4 squared, right? So if that number down in the bottom is the square of something, then you can do this formula for it. And in fact, even if it's not the square of something, I mean, it is the square of something. It may not be a nice number. So even if you have something like 1 over 7 plus x squared, the integral would be 1 over root 7 inverse tan of x over root 7, right? So even if it's not a nice looking square, you can still always just... Sure.
Can we apply this formula basically in any situation where we're looking for an integral that has 1 over something, x squared plus x squared?
1 over any constant plus x squared. Yeah, this will apply. Yep. If there's extra coefficients down here, if it was, say, 1 over 7 plus 2x squared, then you have to do an extra trick where you absorb the 2 into the square, like we did before. Yep.
Once you're able to get that 2 inside that box, maybe write that formula out and start inserting pieces into it and geometry and stuff?
Yeah, yeah. It's a nice little formula. Yes.
If x was to the third, to the third, what would you do then?
Then you're screwed, really.
No, no, but just in general. Like to get it back to.
You can't do it. Like this formula won't work if it's a cubed, and I mean, maybe there's some other form, like probably it is known to mankind what the integral of that is, but it's not. There's no simple trick that will solve that, unfortunately. Yeah, integrals are very tricky in a way that derivatives are not. Like in theory, you can do the derivative of anything just by using the product rule and the quotient rule and the chain rule. But even these formulas here, if you change this power slightly, it just totally messes it up, and the answer will be something completely different.
Doesn't it have to do with the fact that the integral is like, it's a more arbitrary figure and it's more of a representation because it's not for like the tangent function, it's not the entire inclusive tangent function, it's a specific piece of it. Is that kind of why you can't really manipulate them as much as a derivative? Because a derivative, if you're just basically taking a function right there and changing it in a way, on your slope of your tangent, and there's always has to be tangent line.
Yeah, I don't know. I don't really. The fact that this is an inverse tangent, which is only a piece of the full tangent function, I would say that's not quite what makes the integral harder to do. I'm not sure.
I'm just generally a little confused, but I think that's just me.
Yeah. Yeah, I mean, integrals are harder to do than derivatives for other reasons, I would say. All right, excellent. This is all I wanted to say about the inverse trig functions. Any last thoughts about that? We got about 13 more minutes. We can get started on the next section. The next section is something that probably you also have not seen this before. The one after this, maybe you have seen before, but we're going to talk briefly. We're not going to go into super detail about this, but I wrote that wrong. Hyperbolic is what I'm trying to write here. Hyperbolic trig functions. This is something that maybe you've seen these before. Like as buttons on calculators or something. Most calculators don't have a button for this, but I am referring to functions that look like this. Sine with a H after it. You ever seen that?
Oh, it's Cinch, quotient.
Yeah. Oh, maybe you have heard of these before.
Calc 1, baby.
Oh, you talked about these in Calc 1?
Barely.
Hmm.
Yeah, then we went over for a week.
Yeah, we did it towards the end of the semester.
For a week.
I mean, not
Okay.
much, not much.
I was going to do for a week. All right, we'll talk about them briefly. Maybe.
It was a slow class, that's why we did it.
Okay. All right. Yeah, I will pretend like you've never seen these before. This is called the hyperbolic sine. The hyperbolic sine function, and it is pronounced cinch, which sounds really stupid to me. I don't know if anybody feels the same way. There's the hyperbolic cosine, which is pronounced cosh, because it looks like cosh, I guess. The first one doesn't really look like cinch. There is the hyperbolic tangent, which is pronounced tanch. And then we have, of course, the other ones, the secant, the hyperbolic secant, which is pronounced Cinch. And then there's cotanch and cosinch. I always feel foolish when I'm saying these words out loud. These are the hyperbolic trig functions. And we're going to talk about what they mean, what they represent, and also sort of why they are, what the relationship is between these ones and the sine and cosine. Because on the surface, they look completely different from the ordinary sine and cosine. And when you see the definition of these, I think an immediate question you should have is, why would anybody ever think that these have anything to do with the ordinary sine and cosine? Because they really are totally different. These are the hyperbolic trig functions anyway. Let's just talk about the definition for Cinch and Cosh. We're mostly going to focus on Cinch and Cosh. Here's the definition for Cinch. It is e to the x minus e to the minus x over 2. So one immediately nice thing about Cinch as opposed to the sine function is Cinch just has a formula, and if you want to know what the cinch of something is, you just plug it into the formula. Unlike the sine, if I ask you, like, what is the sine of 32 degrees, you really have no formula you can plug that into. You can type it in your calculator, but there's no way by hand to figure that out. Cinch, it just has this formula. And Cosh has a similar formula. The only difference is that plus in the middle rather than the minus. All right, so these are the definitions of Cinch and Cosh. And like I said before, the foremost question in your mind should be, what does this have to do with sine and cosine? Because these definitions don't look anything like the definitions for sine and cosine. And there is, Cinch and Cosh have nothing to do with like the opposite side and the hypotenuse side or anything like that. They have nothing to do with triangles at all, really. Let me just, for the sake of completeness here, tell you what the other definitions are. The other definitions are sort of what you think they should be. So, Tanch, the definition is Cinch over Cosh. Just like the ordinary trig functions, really, we mostly are going to try to understand Cinch and Cosh, and then all the other ones are related to them. So there's also Cosinch, which is 1 over Cinch. They are all the same relationships. There's Cinch, which is 1 over Cosh. And there's Cotanch, which is 1 over Tanch, which of course is also Cosh over Cinch. All right, these are the trig functions. Tanch, yeah, that's how you say it. Yeah. You could put the C in there if you want. Your calculator probably doesn't have its own button for these, but like if you go down in the menus somewhere, you can find these functions are built into your calculator. Or you can always just use the e to the x to do it sort of by hand. Let's talk about the graphs of these things. If their definitions do not in any way resemble the ordinary sine and cosine, perhaps the graphs look like the graphs of sine and cosine. Spoiler alert, they do not. They don't look like the graphs of sine and cosine, but we'll try and explain them. So let's talk about Cosh first. So Cosh, just because it's a little easier to see why the graph looks like this. I mean, you can graph this on your calculator if you want to. If you write this instead as 1/2 e to the x plus 1/2 e to the minus x, Cosh is a combination of e to the x and e to the minus x. And if you were to graph those two things together, they look like, e to the x looks like this, of course. So let's say this is 1/2 e to the x. It'll go through 1/2 here, right? And then 1/2 e to the minus x is like that, only it's reflected horizontally, because if you swap x with minus x, this is reflecting all the x values. So this is what 1/2 e to the minus x looks like. And the graph of Cosh is what you get when you add those two graphs together. So it looks, I'll draw it in red here. It looks like this. It's sort of floating above either one of those. And in fact, if you look in the limit, this red line approaches the black lines on either side because the other thing you're adding it to is like close to 0. So this kind of, these are all curves, but the red one sort of asymptotically approaches these other curves.
And what is that? What's the function for that one?
This red one is Cosh. That's the graph of Cosh because it's those two black lines added together. So you're adding the y values, which makes it higher up, but only a little bit higher up on the two ends because the things you're adding together are very close to 0. All right. So the graph of Cosh, I know that's kind of a sloppy picture, but anyway, the graph of Cosh looks like this. It is not periodic. That is, it doesn't like go back and forth the way that cosine does. Which, if you ask me, that's like the whole point of sine and cosine from a certain point of view is that oscillatory behavior. This is why sine and cosine appear in nature. You're describing motion of waves and such. Simple harmonic motion, movement of springs or whatever. Those have to do with sine and cosine because of that back and forth. The Cosh does not go back and forth at all. For similar reasons, I'll just tell you what the graph of Cinch looks like. It looks like this. In this case, the Cinch is approaching e to the x on, or 1/2 e to the x on the one hand, but negative 1/2 e to the x on the other hand, and so it has this different kind of shape. Looks maybe vaguely like the graph of x cubed, but it's not the same. Or it looks also vaguely like arctangent, the inverse tangent, but it doesn't have asymptotes. It does. Oh yeah, tangent, not the inverse tangent. It looks like the middle piece of the tangent, but the tangent has asymptotes, vertical asymptotes. This one doesn't. So it actually does go on forever, on either side, but it increases exponentially. Yeah, so Cinch is up here, e to the x minus e to the minus x. If you wanted to write, like, sort of factor out the 1/2, it would be 1/2 e to the x minus 1/2 e to the minus x. Minus rather than plus, which is why one side of it goes down and the other side goes up. All right. And then the Tanch, I will just draw the graph of Tanch. This I'm not going to try to explain why, but it comes from dividing those two things. This one actually does look like arctangent, but it's not the same. But these asymptotes for the Tanch are 1 and -1, and it looks like this. I wouldn't necessarily suggest you remember what these graphs look like. You know, I think it is important to know what the graphs of sine and cosine look like, but Cosh and Cinch, maybe not so much. All right.
And then tangents will be negative when you also.
Those horizontal asymptotes are -1 and 1. Yep. Right. Maybe we've only got 2 minutes left. I'll just tell you in our remaining 2 minutes where these occur in nature. Anybody know? You guys who've heard of these before? There's sort of one example that everybody talks about, if you talked about it at all. Maybe you didn't. Sure, yeah. I don't know. Maybe.
Sound.
This is not what I was thinking. No. Again, maybe it has to do with that somehow. The graph of Cosh actually appears in nature. I'm sure you saw something related to the graph of Cosh if you walked to class today. Cosh, so the shape of Cosh has a name. It's called a catenary curve. So it looks kind of like a parabola, but it's not a parabola. It's a catenary. And a catenary is the shape that a hanging rope will naturally settle in. This kind of U shape. It looks kind of like a parabola, but it's not. If you catenary, that's a Catenary. All right. So if you see, power lines or any kind of hanging thing, like even if I just do this right now, well, this is pretty rigid, but it is actually not a perfectly straight line because it will sag to some extent, and it sags according to the shape of a Catenary curve. So it's the shape of a hanging rope. And this is important in rope. In architecture, say if you want to build a bridge, the natural anything that you build will sag, and you can put supports under a bridge, but even in between the supports it will sag, and it sags according to the equation of a catenary. And so oftentimes, to counteract the sagginess, you will build your bridge, you don't make it straight, you make it sort of bowed upwards a little bit so that it will sort of sag into position, and you want to bow it upwards in the shape of a catenary so that it naturally counteracts.
There's like a story of the news actually like completely regarding that. There's like a bridge in California, this is like 10, 15 years ago. When they built it, it spans a river. And when they built it, they didn't account for the wind because the river goes, it's basically a cut through the rock and the wind shoots up the river. And so they didn't account for the wind, and so the bridge began to sag down into the like kind of created catenary shape. It like caused the wind caused the bridge to support the top, and the bridge just get blown off and
Nice. Yeah. Yeah, so anyway, these are important. It's also, you can see this in some architecture, like the St. Louis Arch looks like that, which looks vaguely like a parabola, but it's not. It's a catenary, and it's because a hanging rope, it hangs in this particular shape because this is the shape which equalizes the tension throughout the entire rope. If there was extra tension somewhere, it would slack out the rope and it would settle into a catenary. So if you want to build a stable arch which is only anchored at 2 points, you want to build it in an upside down catenary because then the tension in the arch will be equalized throughout. That's called a catenary arch, which most arches in architecture are actually built like with straight up and then some kind of arch towards the top. That would not be a catenary because all of this extra stuff modifies the physics of how it works. But if you want just a pure arch with 2 anchor points, the catenary is the shape. All right, I think that'll do it. Have a good weekend. See you next time. Goodbye to the folks back home.
Do you mind taking a look at this guy
Sure.
over here real quick? So I obviously wrote it incorrectly. Didn't even write the right problem down. With aviation moment.
No, this is all correct given your misinterpretation of the original problem.
Yeah. So yesterday, if you want to like, I was definitely struggling, and you saw in my first quiz I struggled with the washers. And
Yeah,
stuff.
yeah,
And so we're not letting that happen again. And so I went through yesterday and I redid all the problems from the homework, and then I went through and I just like